Hello, everyone. I thought probably you'd want to go over this worksheet because I know some of the questions were fairly difficult. Some of them I know, though, were very easy for you as well. All right, so let's begin with, do heavy things fall faster than light things? And you were doing a thought experiment by standing at the back of some bleachers, football bleachers, and dropping things so that they fell quite a distance. And we were comparing a feather and a baseball, which would hit the ground faster and why. Well, in your thought experience, I suspect the feather moved back and forth in the air. Back and forth in the air. It's so light. And has so much surface area. Right? Air resistance. Is an enormous factor. All right, baseball. All right, the second one says compare a baseball and a softball. So a baseball, is about this big, and a softball is about that big. I think I probably have the size right, but both are fairly heavy. All right, the two balls are not identical in weight, but similar. In weight or size, but very similar, right? Both are spheres. All right. Air resistance shouldn't be much of a factor, should it? So I'm wondering what you wrote. Well, I'm saying the same. In fact, all objects that are not affected much by air resistance, like a flying squirrel, for example, all of them would fall at the same rate. All right? So all objects fall at a rate of 9.8 meters per second squared. The acceleration due to gravity, right? All right, so the only exceptions would be things that the air resistance really grabs hold of, like a feather. So this is Galileo's experiment, supposedly, from the Leaning Tower of Pisa, in which he dropped things. And as he thought about it, he realized that most things would fall at the same rate and hit the ground at the same time, except for things that were easily affected by air resistance, like a piece of paper would be. All right, so all objects should hit the ground at the same time. All right. A force is required to get a ball rolling or to stop it. Explain this. Well, according to Newton's first law, all right, the first law of motion, all objects will stay at rest or move in a straight line at the same speed unless they are acted upon by a non-zero net force. Yes, it's the first law of motion. So all objects at rest stay put. Moving objects stay at the same speed and direction, right? Move at same speed and direction. Unless acted upon by a net force. By a non-zero net force. Oftentimes there's multiple forces acting on any body. So that's why we say net force. That we might have to figure out, well, what all is acting on this object? Is there more than one force? Is there no force? Is there a net force of 0 is no force then, right? All right, now units versus variables. Units are how they're measured. The variables are things like A, M, T, V, D, where they stand for, respectively, acceleration, mass, time, velocity, and distance. All right, variables are used in equations, right? All right, and are measured in science, all right? So the units are how they are measured. Yes, such as distance can be measured in inches or meters, as we know on our meter sticks, but in science we use metric, and the primary metric measurement for distance is meter. All right, so the kilogram measures mass. So when we determine mass, we measure it in grams on a balance, kilograms on a much larger balance. The Newton measures force, so that can be the force of weight. All right, applied force. All right, contact force. Yeah, like these are contact forces or at a distance forces as well, such as gravitational force, such as the electrical force of attraction or repulsion. All right, they're all measured in newtons. Meters per second squared measures acceleration in the metric system, where meters is the unit of length and second is the typical unit of time. And what is speed? Well, speed is just distance traveled divided by time. All right, now, to have velocity, you must have a speed and a direction. Sometimes all we say for the direction is straight. Sometimes we say perpendicular. Sometimes we say it went off on the vehicle veered off in a diagonal. All right, sometimes we say the opposite direction. All right, we don't always specify exactly a degree amount, like made a 45-degree turn. We often just say a right turn, a left turn, veering off at a diagonal. We'll often use words that are such as that to describe the direction of velocity. Find the average speed of a cheetah that runs 10 meters in 4.0 seconds. So I added the 0 so we would have two significant digits. Well, the average speed is always the total distance by the total time. The cheetah went a total distance of 100 meters. And the time it took, the total time, was 4 seconds. Cheetahs are the fastest land animal. That's one of those facts I have in my brain. All right, and so I rounded it to 2 since this was 4.0. All right, I always mean to give you numbers with more significant digits for that reason. All right, 25 meters per second. And see how we get that unit from the equation. So essentially, we are doing calculations on the units as well. All right, what is meant by net force? Net force is the sum of all the forces acting on an object, acting on one object. All right, so I just put an example. What if you had 3 and we had this box right here? All right, what if we had these 3 forces? All right, so the net force is all the forces acting on an object. Later on, we'll talk about how to measure it. All right. 11, define acceleration using words and formulas. Well, I said that acceleration is change of velocity. That's its standard definition over time. It could be a change in direction or a change in speed. It could also be both. You frequently change speed when you go around a corner, don't you? If you're wise. And then formula-wise or equation-wise, I tend to use the word equation. Delta V, the change in velocity over time, and that's usually calculated by the final velocity minus the initial velocity over the time it's taken. All right, now describe acceleration in relationship to force. Well, acceleration happens when a force is applied. All right, that is the standard understanding in physics. Both acceleration and force are vector quantities with an amount and a direction. All right, so the direction applied by the net force is the same direction the acceleration has. All right, so, and you realize that if you push a kid backwards, then the direction of their acceleration, change in velocity, is backwards as well, right? All right, so the force is equal to ma, right? That's Newton's second law. Force equals ma. So is the equation to calculate the amount of acceleration of an object of known mass. All right? By a certain size force. All right? So Newton's second law is the connection between force and mass. All right. Now remember, you can stop the video whenever you need time to write things down. Describe how mass and inertia are related. Well, this is essentially Newton's first law. The mass of an object at rest is a measure of how much the object will resist motion, and inertia is defined as the resistance to moving. All right? An object in motion resists change to its speed and its direction. All right? And so the mass, it's essentially is involved in the inertia of both one object that is still at rest or an object in motion. How does mass affect acceleration? Well, once again, we have Newton's second law, right? The greater an object's mass, the smaller its change of velocity. And we know that if you give the same size shoved to a big man and a little kid, that the kid is going to change velocity a lot more. So the greater an object's mass, like that of the man, the smaller the man's change of velocity, whereas the smaller, like with the child, an object's mass, the more it will change velocity. All right? The greater an object's mass, the smaller. So these, if in the equation of the second law, F equals ma, the mass and acceleration have an inverse relationship. One goes up, all right, as mass increases, then acceleration decreases. Why can I say that air resistance, for another example, if the mass is half as much, like let's say, for the same size force, if the mass is half as much, the acceleration would double. That's how you do inverse. If the mass is 1/3 as much, then its acceleration would triple. Why can I say that air resistance is a negative force? Well, air resistance supplies friction, right? Yeah, it's one of the main, besides friction with the road, air resistance on a car is what changes the gas mileage you get. All right. So it causes the car to slow down, and that means you don't get as good, you don't cover as many miles in the same amount of time or on the same gallon of gas. The force of friction opposes motion, therefore it slows the speed of a vehicle. All right. And so you have to say that it's a negative force. And 16 asks the corresponding question, what force always resists or opposes acceleration or motion in general? And the force of friction is the answer for that. It opposes motion. All right, so if we have an object, all right, and we push a force on it, we would always say, in this case, we would probably be saying that the resistance is not resistance with the air, but resistance with the surface. So that the force of friction is in that direction, whereas the force of movement applied is in that direction. All right? And so you can see why you would consider friction a negative force, wouldn't you? Because it always opposes motion. That's its definition. All right, how do we find the net force from three forces acting in different directions? Well, we add them. If all the forces push in the same direction, the net force is the simple sum. If the forces push in different directions, at angles, we do vector addition to figure that out. And if the forces oppose each other like friction, we subtract them. All right? We subtract them. All right, so let's do, if we have two forces acting on this object, let's say we have a taller person and a shorter person acting, all right? And this is 25 newtons, and this is 10 newtons. The fact they're going in identical directions, the net force is 25 plus 10 newtons, right? Or 35 newtons. However, if we have a frictional case like up here, all right, and the force applied is let me not use that example. We'll come back to talk about that at a later point. All right, now, the other way that we talk about it is, let's say we have this object, and then we have a force acting at this direction, a force acting at this direction, and then a force acting at this direction. All right? We'll call this force 1, force 2, force 3. What is the sum of those forces? Well, you can't simply add them up. So what we're going to do is graph them. So I'm going to start with force 1. All right? See how it's this long. And here was the origin. That's where we started. And then I'm going to do the second one, which goes straight. And it's a little bit longer. A little bit. That means it's a bigger force. All right? And then I'm going to do the third force, which is at this angle. Whoops. I think I'm a little off on my angle. Let's make that just a little better. All right. All right. Well, what happens is that we end up adding head to tail, like we plotted our vectors, remember? So we plot these three vectors, head to tail, and then the actual force is the distance from the origin to the end of our force. All right? So this resultant is the vector sum. All right? You can do this with trigonometry as well, sine and cosine, etc., by figuring out the angles in each case. But it's awfully easy to graph them, just as we did. And we can see that then instead of the sum being however long 1 is, plus however long 2 is, plus however long 3 is, we can see the fact that they had different angles means that the vector sum is less, isn't it? Is less than a simple sum. Because they're not all going in the same direction. Like we saw over here with a tall person and a short person pushing. But see how they did this at exactly the same angle. Whereas these guys, whatever force was acting here was coming from the bottom. This one was coming from the top, and this one was straight on. And so we would have to do a vector sum. All right, let's go down and see what else. What unit is used for force? Well, we've already said it's a Newton. And a Newton means a kilogram times a meter divided by seconds per second. All right? That's its definition. And it's named after Isaac Newton. The force that holds you up is called the normal force. It acts opposite to the force of gravity pulling you down. So the normal force, is up and perpendicular to the ground. To the surface. And it's a force up. What is velocity? Well, it's a vector quantity measuring speed and direction. The metric unit is meter per second. So we measure it. The variable is V. The metric unit is meter per second. That was a repeat question. All right, now we have a bunch of things where you can imagine Tiffany. She's hanging from the rings of the swing set. Her weight is 150 newtons. So what is the tension in the chains? All right, so the tension in the chains, if she weighs 150 newtons, all right, her weight, the force of her weight is down. And so the chains have to pull up. All right, the tension in the rope has to be pulling up. All right. But it's the same size, exactly. If she weighs 150 newtons, all right, she's hanging from that, and the force of gravity is acting on her, right? Yes, but she's not falling because the tension in the chains is in the opposite direction. All right, and pulling her up. Let's say I am pushing on a large box with 200 newtons of force. All right, Clint is pushing on the box in the opposite direction. Well, that's not very helpful, is it? Why won't the box move? Use the word equilibrium. Well, there's no movement with the net force. All right, equilibrium is a state of non-movement. Due to net force, due to the forces adding up to zero. Yeah, so we didn't use that word, did we? Equilibrium. Yes, equilibrium is simply a state of non-movement due to forces adding up to zero. In chemistry, equilibrium is also a state of no change in concentration of reactants or products. So it's a state of no change in motion. All right. And in this case, there was no movement with no net force, so the object is at equilibrium. Newton's third law talks about an action and reaction force. The action force is first and acts on an object. The reaction force is the object pushing back with the same amount of force and acting in the opposite direction. All right? They're called a pair of forces. So here's an example that's interesting. If a cannon is fired, use A equals F over M, acceleration equals the force divided by the mass, to explain what happens to the cannon and the cannonball. Well, a cannon is fired for the purpose of accelerating the cannonball in the direction, whatever direction the cannon is pointed, right? And a cannonball is a projectile, right? Is a projectile as soon as it's shot. All right. What I might do, let me just change colors so that we can see some difference when I add something to this. Okay. All right, so a cannonball is a projectile. So we know that it's going to go up and then it's going to fall down. All right. So a cannon is fired for the purpose of accelerating the cannonball inside of it in the direction it's pointed. The force is delivered by an explosion inside the barrel, right? The greater the force on the cannonball mass, the greater the acceleration. All right, since the acceleration depends on the force divided by the mass. All right, so if you add more mass up here, all right, that means you would get a greater acceleration. All right. the smaller the cannonball's mass, the larger its acceleration. So once again, if we say the force stays the same, but the mass shrinks, all right, so these go together. If we say the mass shrinks, but the force stays the same, well, then we have a larger acceleration too, because the number in the denominator got smaller. Fractions are larger when the number in the denominator gets smaller or when the number in the numerator gets larger. All right. Newton's third law of motion states what? That for every action there is an identically sized force in the opposite direction. The pair of forces act on different objects. All right? Same sized forces in the opposite direction. Just like we said with the chair and the person sitting on the chair. So the person sits on the chair with the force of their weight. Let's say, we'll use some English units, pounds. Let's say with 100 pounds. Well, the chair pushes up back at you with a force of 100 pounds. All right? But one force is on the chair, and the force up is on the person's rear as they're sitting. Okay, so when two forces act on one another, it's called an action-reaction pair of forces, and this is Newton's third law. Now, we're back to these crates again. Jordan is pushing with a force of 50 newtons on a crate, and the friction forces are 100 newtons. Will the crate move? All right. Well, no, because he isn't pushing enough at 50 newtons to overcome 100 newtons. All right? But the frictional force doesn't push the object backwards, and that's what I wanted to say. Doesn't push the object backwards, does it? It doesn't push the object backward. No. It simply keeps the object from moving. All right? So force of friction. So we're not subtracting. That's why I didn't do that subtraction up there before. Because there still is a force. There is a difference here, and so the object will not move. But when the object isn't being pushed, then there is no force of friction. All right, the force of friction exists when the object is in motion. So in physics, we often draw, and we use a combination of equations, sentences, and drawings. All right, so that's the way I'm teaching it. All right, so the acceleration of the crate is 0. The acceleration due to gravity is what? Well, 9.80 actually meters per second squared in the downward direction towards the surface of the Earth, correct? Acceleration is delta V over delta T. In words, this is said as a change in velocity per time of the change over which that velocity was occurring. All right, the time of the change. How long did it last? How long did the change last? So the delta sign in chemistry and physics simply means change. As a motorcycle climbs a hill, why does it undergo acceleration? So I drew this picture. Now, as it makes this and goes up, right, it's changing its direction, is acceleration, all right? That's why it undergoes acceleration. It's changing direction of travel, all right? If it went straight, it would be going that way. So that's if the object slows down going up the hill, depending on how you interpret this question. If it slows down, that delta V is acceleration, but it's a negative acceleration. Slowing down is a negative acceleration, but it's still an acceleration. All right, so if the force of weight is 100 newtons down, then we know the force of the table is up, right? Is up. The force of weight acts downward with 100 newtons. The table pushes up with a force of 100 newtons on the box. All right, so we have a box here that they're referring to. All right, and you put it on the table, and its weight is 100 newtons. Remembering that weight is a force, the force of weight. All right, so it acts downward with 100 newtons, but the table pushes up. And this is called a normal force. All right, the force is 100, then we know the force of the table is also 100 newtons. All right, now the reason this was a little hard to interpret, so I answered both questions. All right, so the force of weight acts downward on the table all right, with a force of 100 newtons. The table pushes up on the box with a force of 100 newtons upward. All right, up, down. So the interacting objects, the interacting objects are the box and the table. So the box pushing downward on the table is the action force. The table pushing up with the same amount of force is the reaction force. All right? That is the reaction force. All right, now we have this person named Caitlin, and she pushes with a force of 125 newtons, and the crate does not move. So what does that say about the frictional force if that happens? Well, the frictional force must be greater than 125 newtons, or else she would be able to move it, correct? So the friction opposes any movement of the crate, of the crate. Friction only acts when you push on the object, all right? And get it moving or try to get it moving. Now, the next one says a force of 204 newtons is applied to an 18 kilogram block. What's the acceleration? Well, assuming that 204 newtons is the net force, so if all the forces acting on this block, the net force is 204 newtons. And the mass is 18 kilograms. Well, I then assumed, since F equals ma, that F equals ma, so dividing through by the acceleration on both sides, all right, we get the force divided by the acceleration should tell us the mass. Or, what is the acceleration of the object, or the force divided by the mass equals the mass times acceleration divided. So these are ways to rearrange the equation. All right. What's the purpose then of rearranging the equation? Well, we want whatever we're looking for to be on the side by itself. So in this one, we want to get acceleration by itself because that's what we're trying to solve. And that means we just take the force and divide it by the mass. All right, so that's what I did. This is 204 kilograms. Whoops, let me get this over. All right. And that's a newtons, 204 newtons is a kilogram meter per second squared, 204 of them, divided by 18 kilograms. And then you can see how we get this unit of acceleration in our final answer. All right. And I did the calculation over here and got 11.333. All right. So let's say we actually measured that and it was 18.0 kilograms. Then, if we had 18.0, we could round this to 3 numbers. So this is the reason whenever we measure, we try and get the most numbers we can, because then our answer, instead of just being 11, we can say 11.3. And doesn't that seem a lot more satisfying? And by changing a newton to a kilogram meter per second squared, we were able to cross that out here and here and get meter per second squared as the correct unit for acceleration. That's another way we know we did the problem right if we get the right units. All right, now (35) says a 2 kilogram steel block is moved across a table at 0.25 meters per second squared. So how much force caused that? How much force was applied to cause that? So what I did, I'm going to do the same thing and add a unit. Say, I would never make a 2 kilogram measurement. It would be 2.06 or 2.452, something like that. So that's the reason I always add numbers to make this seem more reasonable. So that kilogram says that's a mass, so I labeled it that way. The mass equals 2.0. If it moves across the table at 0.25 meters per second squared, well, this is the unit for acceleration, right? So that's how I knew that variable is acceleration. So I have the mass and the acceleration and need to find the force. So by the second law in its regular old form, I just multiply 2 times 0.25, all right, 2.0 kilograms times 0.25 meters per second squared, and that gives me 0.50 kilograms times meters divided by second squared, and that's the definition of a Newton. What force is needed? So remember, you can always stop the video and listen to me explain it again, or just to look at what I did a little bit longer. That's the benefit of doing a review in a video. Okay, that's one reason I like to do reviews and videos. What force is needed to accelerate a 200 kilogram mass across a surface at 75.5 meters per second squared? Wow, that's a lot of acceleration. And this is a big mass, 200 kilogram mass. A kilogram is about 2.2 pounds, all right? Yes. So that's about a 440 pound mass. All right, it's equivalent to a 440 pound mass. So that will help you realize. So getting this going at that speed, wow, there's a big force needed to do this. All right? All right, so 200 times 75.5, well, 2 times 75.5 is 151. And then there's these two zeros. All right, so then I added those two zeros because we can't have no more than 3 digits in any of our measurements, right? So since our answer can't have any more than 3 digits, we have to use these zeros. If we don't put in the zeros, it just says 151. So when we want to keep, they're called placeholders because we want to keep this at a value of 15,000 newtons. And the only way we can do that is by adding those zeros as placeholders. All right, they don't count, though, as significant numbers. All right, but they're necessary for placeholding. All right, now a force of 12.5 newtons is applied to a 10 kilogram mass. This tells us we have a force and a mass. So what's the acceleration? Well, we divide through F equals ma, like we did above, and we get the acceleration then is the force divided by the mass. So F equals ma, let me remind you again. I want to have acceleration by itself so I know exactly what I do with those numbers, 12.5 and 10. All right, so I'm going to just divide through by whatever it is that I want to get by itself, in this case, that. All right, so I'm going to divide through by the other variable that's in the way, all right, and then I get ma divided by m, all right, and this cancels. That's how you rearrange an algebra. So I wanted to get acceleration on one side all by itself. To do that, I have to get rid of m. So I actually divide through by m first on both sides. All right? So 12.5 divided by 10 kilograms. All right? And so once again, I'm saying I wouldn't just have 10 kilograms. I would have 10 point, more than that, probably 10.021 or something. So at least let's give it one more digit. All right, 10.0. And then we can have, the answer would be 1.25 when we do the math. And the unit left after the kilograms cancel, meters per second squared. And that is the unit for acceleration. So getting the right unit is a check on your calculation and setting up of the problem. All right? Now, 38. If an object is moving with a force of 99 newtons at 12.5 meters per second squared, once again, that must be an acceleration. This, though, tells us it's a force. What's the mass? Well, in this case, with equals ma. I want to get the mass by itself, right? So I'm going to divide through to get rid of acceleration, but I have to divide by acceleration on the other side as well. So F over A equals the mass I want. So I take the two numbers I'm given in the problem, and it tells me I need to divide them with 99 on the top. So 99 divided by 12.5. All right, we have two digits in 99, so our answer is limited to 2. So I took 7.92 and rounded it to 2 digits. And see how the unit left in this, after we do the math of canceling them, is kilogram. All right, you were pulled to Earth by the force of gravity. What is the weight of in newtons of a 55 kilogram mass? All right. This, you know this, but you may not pull it together. So, the force of gravity acting on you, right? The force of gravity acting on you gives you an acceleration towards the Earth. All right, and we call that G. So, where it says F equals ma, the acceleration due to gravity, all right, let me see if did I solve this anywhere? Oh, yes, I did. All right, so then what I did was take this equation, which is F of weight equals m times g, and I multiplied the weight of 55, the mass, 55 kilograms times 9.8 meters per second squared, and that's how I was able to get those units. All right, so the force of weight equals your mass times the acceleration due to gravity. Weight is a force. Then your mass is all the stuff you're made of, right? And then G is the acceleration due to gravity on the Earth. If you were standing on the moon, you would have a different weight because the mass would be the same. You'd still have the same amount of stuff. But the gravitation on the moon is the force of gravity is much smaller on the moon because it's a much smaller planet, right? And because it's a smaller planet that circles the Earth, it's called a moon. All right, moons by nature are smaller. All right, the big mass is the one that has moons that rotate or that revolve around it. All right, so this is the equation that involves weight and the force of gravity on you. So your weight is the force of gravity on you. On you. And you know how we always wrote this as force, and then we gave it a little g for gravitational force. All right. So that's the force of gravity. The acceleration due to gravity is g. The acceleration, the change in your velocity over time, is g, due to the force of gravity on your mass. All right. Now, the last one is just another problem involving this. So I just made the comment again. What's the mass of a person whose weight is 110 newtons? Then, all right. So this was a little bit different. So we have force equals mg, right? But the question says, what's the mass of the person? So this is the variable we want alone. So I'm going to divide both sides by G. Yeah, see how I did that? So I could get rid of it. All right, so the mass is equal to the force over the acceleration due to gravity. And so that's what I did in this equation. 110 kilogram meters per second squared divided by 9.80 meters per second squared. I put the 0 on so I could have 3 digits in my answer. So remember, you can go back and look at anything that you realize you still don't understand very well and hear me explain it again. All right, now, if I was going to go over these, why did I ask you first to do it? The reason is I wanted you to think about these things and realize what you knew and what you didn't know very well. All right? Then you're much more alert when I go through a video explaining things. You're saying, "Oh, that's why that happened," or you're saying, "Oh, I didn't realize we were talking about Newton's third law," or any of those things. You know that it's important to realize what you know and what you really don't know, and so hopefully this review has more meaning. So that's the method in my madness. All right. All right. Talk to you soon. Adios. Tomorrow, by the way, I think what we'll do is finally analyze that data. All right, that we did of the falling objects in your videos. All right. Bye.